Hi everyone, I'm Maurizio Rea from Ninja Networks, and today I'm going to present you a Bielsa strategy for millimeter wave networks with out-of-band input data. But let me first start with the motivation of the work, because as we know, millimeter wave communication supports physical data rate up to several gigabit per second, but using directional phase antenna arrays. And the communication between the access point and the user requires the link establishment needed to find the angle of departure at the transmitter and the angle of arrival at the receiver in order to select an antenna sector pair that allows to establish the communication and at the same time to maximize the received power. And then we have the link maintenance, which is actually a continuous beam adaptation needed to maintain higher data rate due to, for instance, some environment variations or user mobility and rotation that change the link quality. Then we have the access point handover, which is the procedure needed to increase the data rate if there exists another access point able to do that. And so all those procedures together require time, increasing the latency during the communication. And so what we propose here today is to speed up the communication using context information. And so doing so, we don't need for explicit beam training. But let's see now, let me explain you now what is the beam training. And as a reference, we take the IEEE 802.11 AD standard for the beam training. This standard handles the beam training via a sector level sweep strategy. And here we can see an example. More specifically, the SLS comprises two different phases, well, two phases, and the access point SLS and the user SLS. During the access point SLS, as you can see in the picture, the access point switches across all the sector and transmit training frames marked with sector identifiers. And so in this case, we have 16 different sectors with the numbers, as you can see, the beam training times lot, and each sector has its identifier. And during this procedure, the user receives those frames with the omnidirectional antennas pattern and identify the access point sector with highest received signal power. Then, of course, the same procedure is the same procedure is repeated for the user, as you can see here. And for instance, in this example, the communication between the access point and the user, it's gonna be through the sector 4 and 12. Okay, then after seeing the beam training, what we propose here is to speed up, as I said, using context information, most specifically estimation of angle of departure, angle of arrival pair by using sub-6 GHz Wi-Fi technology, which is possible, of course, in a multi-band device. In this area, we have seen that previous approaches are affected by three main problems. Let's see one by one. The first problem is using an access point with a few elements in the antenna array, a median error in the angle estimation about 20 degrees is 20 degrees more or less, meaning that a further refinement is necessary to align the antenna beams. The second problem is the angular rotation. Any variation of the angle must be compensated, otherwise the millimeter wave link quality will suffer dramatically. And for this purpose, what we propose to use is the output of inertial sensors such as compass and gyroscopes. Then there is the third problem, which is the handover procedure at millimeter wave, which is typical in very dense network with multiple access points, where the client is connected to one access point until the connection is below the sensitivity before starting a new search for another access point in range. And for this problem, what we propose is to investigate a technology, sub-6 gigahertz technology, that can provide a distance estimation, such as, for instance, the new protocol fine-time measurement provided by the standard 802.11nc. And so, having an idea, what we propose here is a slash our Bielsa strategy for millimeter wave link establishment and maintenance, where we use as inputs, we use the output of an inertial sensor and sub 6 gigahertz angular information provided by this work, where we fix actually the angle error of about 20 degrees. Let's go into the details, where we can see here for link establishment, we start first with the access point SLS as a first step. And the access point can use the user estimated direction, as you can see in the black line, angle of arrival, and then fixing the angular error of theta of 20 degrees, the angular region of 2 theta is used to find the subset of sectors for the axis point SLS. So in this case, instead of using 16 sectors, we are using only 4, 3, 4, 5, and 6. Then, for the user SLS, we also investigate the similarity of the downlink and uplink channels, and so looking this time at the direction of the axis point, and so at the angle of departure, we compute theta c, which is actually the angle we correct the direction by this theta c, and then we reduce the number of sectors in the uplink. While for link maintenance, what we propose to update the sector using, as I said, output data from inertial sensor such as the gyroscope for the rotation. Here, as we consider the static access point, the only problem is for the user side that need to update the antenna sector. And so in this case, as you see from the picture, during the user mobility, as soon as the system observes a drop in the signal quality, the estimated angle from a rotation is provided. Now, there are two options. If there is a change in the direction, the new sector, which is the yellow one in the example, is going to be the candidate. If there is no change in the direction, then slash is going to monitor the distance estimate provided by the sub-6 gigahertz system technology, which is the distance estimation from the user to the access point, to see if there is a new access point for the endover procedure. I'll say that we can go to the testbed, where our measurements are conducted in an indoor space, where we have office environment covering a surface of 300 square meters, and you can see with the black lines that we also have concrete walls separating the offices. Here, since we conducted different measurements during for static users and user immobility, what we have, we deployed 5 access points with the red circles, and then 2 different positions, 2 different users with the green crosses. And for the mobility test, actually the user 1 is going to move along the trajectory you can see in the blue line. Let's go into the details about our experimental setup for link establishment. In order to follow the user and the access point SLS in our system, the MillimeterWave transmitter is connected to a signal generator which sends a probe signal, and it is mounted on a motor with an accuracy of 0.18 degrees in order to emulate steerable phase antenna arrays. The receiver is connected to a signal analyzer to measure the received power per beam, and in the IPSLS, the access point uses the 60 GHz transmitter with a 7 degrees beam width, you can see on the left, while the user is connected to an omnidirectional antenna you see on the right. We then have the opposite configuration during the UE SLS. For testing mobility, then, since our mechanical rotation doesn't allow the system to operate in real time, we then use a very well-known ray tracing tool, which is called WinProp, and its integrated graphical editor to reproduce the same office environment. And so here you can see we try to reproduce the same scenarios. We're introducing all the parameters for all the materials. Then we go to the evaluation, and actually our first idea for the evaluation was about the impact of the angle error on the millimeter wave RSSI for link establishment. More specifically, here we fixed the error of around about 20 degrees. And so as you can see here in the figure, we have the receive power per each rotation in degree. And looking at the red cross, which is actually the estimation of the angle of departure or even angle of arrival, if we increase the area of 2 theta, where theta is 20 degrees, and so up to 40 degrees, we are able, according to the example we see in these pictures, we are able to detect the best beam in terms of best RSSI, which is the green circle. Then we move to evaluation for of slash for a static user, where we define first the normalized data rate, as you can see from the first line, and then where R is the achieved data rate, T is the period of 2 milliseconds, and tau is the beam search latency, which is actually very few microseconds. And here we compare slash with other two different strategies. At the baseline, which is actually the standard 802.11ad, and then we also compare with the compressive beam training approach, which adapts compressive path tracking for sector selection. As you can see here from the ECDF of the normalized rate in gigabit per second, we see that slash can achieve a data rate that is 64% higher in median than compressive beam training. Then we move to the evaluation of slash for a mobile user, and we studied the performance with a user moving with a working speed of around 0.5 meters per second, and the rotation of the user is about 0.35 radians per second. And here for this trajectory, you can see the blue line in the plot. Here in this scenario, we are using only the access point number 1 and 2, as the other three access points don't provide good coverage, being in office environment, office rooms. And so here in this case, we can see first of all the distance, real distance in the first plot, the real distance and the estimated distance provided by the sub-6 gigahertz system. And as you can see, there is also the estimation of the angle, the rotation during the link maintenance. And we can see that slash tries to maintain the highest data rate, and the algorithm is called every time the RSSI drops below the threshold for the communication. Here, in this case, we are achieving best performance than other strategy, as you can see in the last plot, where we see the normalized rate in time for different approaches. And so, in conclusion, today, we have seen how context information from out-of-band inputs can be used to speed up the beam training process in millimeter wave networks. More specifically, we also evaluated slash for link establishment, having a median of the data rate which is 64% higher than prior work. Also slash for link maintenance, where we have seen a data rate of 67% and 121% higher than other strategies. And this mechanism can be integrated in multi-band Wi-Fi devices. That's all. I'm happy to take all the questions you may have. Thank you.